Let's be honest for a second. When you look up on a really clear, dark night, what do you see? To most of us, the stars just look like these tiny, piercing white pinpricks scattered all across a black canvas, right? But what if I told you that you are actually staring up at a massive, vibrant, cosmic rainbow? Today, in this explainer, we're going to unravel one of the absolute coolest mysteries of the night sky. We're going to figure out exactly why stars are actually different colors.
So, let's just jump right into the big paradox here. If you pick up literally any astronomy book, you're going to hear scientists raving about red giants, yellow dwarfs, and blue supergiants. It sounds amazing. Yet when you or I step into our backyards and look up, almost every single star just looks, well, white. So what's going on? Is it a metaphor? Are astronomers just making this up? Spoiler alert, no. The colors are incredibly real. And the crazy part is, the reason we don't see them actually has absolutely nothing to do with the stars themselves, and literally everything to do with our own biology.
You see, human eyes are amazing, sure, but they definitely have their limits. We use two main types of cells to see, rods and cones. Cones are the cells that detect color, but they are notoriously light-hungry. I mean, they need a lot of incoming light to actually fire off and send a color signal to our brains. And because stars are just unimaginably distant, their light is incredibly dim by the time it finally hits Earth. It's usually enough to trigger our rod cells, letting us see the star as a little point of light, but it's nowhere near enough to wake up our cone cells. So our brain just takes the easy route and registers it as white. Telescopes and cameras, though, they don't have this problem at all. They can just sit there, stare at a patch of sky, and gather light over minutes or even hours, slowly building up a picture that reveals the true hidden colors of the universe.
And when you do that, the sheer visual proof is just breathtaking. When a telescope gathers enough light, that whole white dot myth is instantly busted. You start to clearly see this glittering array of brilliant shades. We're talking vibrant reds, warm oranges, soft yellows, and these incredibly piercing blues. The universe is actually ridiculously colorful, once you have the right tools to look at it.
Okay, so if the stars really are all these different colors, that naturally leads us to the next big question. What is actually doing the painting here? What determines a star's color? You might logically guess it has something to do with what the star is made of, right? Like maybe a star with a bunch of iron looks red and one with more oxygen looks blue? Actually, scratch that. Almost all stars are made of the exact same basic ingredients, mostly hydrogen, a little bit of helium. The chemical makeup barely matters for the overall color. Instead, the color is driven by one single, insanely powerful physical property. And that property is surface temperature. Now, to truly get how temperature relates to color in space, we actually have to unlearn some of our everyday Earth habits. Think about the plumbing in your bathroom. The red handle always means hot water, and the blue handle always means cold, right? Well, in stellar astrophysics, you have to flip that completely backward. Out in the universe, blue actually means the absolute hottest, while red means the coolest. Think of a blowtorch compared to, say, a dying campfire ember. The roaring, intense heat of a blowtorch burns a crisp, bright blue, while those relatively cooler, fading embers just glow a dull red. To fully wrap our heads around this, astronomers use this foundational concept called black body radiation. Now, don't let the technical jargon intimidate you here. A black body is really just a fancy term for an idealized glowing object that absorbs and emits light perfectly. And stars are fantastic real-world examples of this. The crucial thing to remember is that a star actually emits every single color of light in the visible spectrum simultaneously. But, and this is a big but, it doesn't emit them all equally. Depending entirely on how incredibly hot its surface is, the star is going to emit a massive peak of light at one specific color. And that peak wavelength becomes the dominant color that we end up seeing. If you map this out on a graph, it becomes super clear. A relatively cool star, say one sitting around 3000 Kelvin, its energy peak lands way over in the red portion of the spectrum. It's pumping out a ton of red light and very little blue light, so naturally it looks red. But take a scorching hot star at, say, 10,000 Kelvin. Its energy curve shifts dramatically, peaking sharply in the blue wavelengths. This shift in the peak color, based on temperature, is governed by something called Wien's law, which is basically the ultimate rulebook for star colors. And you can actually see this rulebook in action yourself without a telescope. If you step outside in the winter and find the famous constellation of Orion the Hunter, you can see two completely different temperature stories playing out. Look at Betelgeuse, that star at Orion's upper left shoulder. It has a relatively cool surface temperature, roughly 3400 to 3800 Kelvin, and even just using your naked eye, it has this distinct ruby red tint to it. Now look down at Rigel, down at Orion's bottom right foot. Rigel is absolutely blazing at over 12,100 Kelvin. It is emitting so much energy at shorter wavelengths that it shines this brilliant icy blue-white. Two stars in the same exact constellation, telling us exactly how hot they are just by their color.
Now, all of this naturally brings us to a very personal star, our own sun. If you ask a little kid to draw the sun, they're instinctively going to reach for a yellow or orange crayon. And I mean, that makes total sense. That's exactly what it looks like to us, especially when it's rising or setting. But here's the crazy thing. That is actually an illusion. It's an illusion created by Earth's atmosphere, which scatters away all the blue light and leaves the yellow and red behind for us to see. If you're floating out in deep space, looking at the sun without our atmosphere in the way, it wouldn't look yellow at all. Because it has a surface temperature of about 5,800 Kelvin, the sun's true color in space is a brilliant, blindingly pure white.
But hold on, because here is where the science takes a deeply fascinating twist. If we take that mathematical rule from earlier, Wien's law, and apply it to our sun's temperature of 5,800 Kelvin, we find something super weird. The peak wavelength of light the sun emits is roughly 500 nanometers. And if you look at a standard color chart, 500 nanometers sits squarely in the green part of the visual spectrum, right? So if our sun actually peaks in green, and there are billions of other stars with this exact same temperature out there, why aren't there any green stars? Why have astronomers literally never looked through a telescope and found a glowing emerald-colored sun?
To solve this missing green star paradox, astronomers use this brilliant analogy. It's called the cosmic seesaw. So imagine the spectrum of visible light as a playground seesaw. On one end you have blue light, on the exact opposite end you have red light, and right smack in the middle sits green. When a star is incredibly hot, it tilts the seesaw so the blue end goes high up in the air. When a star is cool, it tilts it so the red end goes high. But what happens with a moderate star, like our sun, whose temperature peaks right in the middle, in the green? The seesaw doesn't bend in the middle, right? It just sits completely flat and horizontal. And when that seesaw is flat, it means a massive amount of blue light and a massive amount of red light are being emitted equally, right alongside the green.
And that completely flat seesaw is exactly where human biology takes over again. Our eyes have three types of cone cells that respond roughly to red, green, and blue light. For us to see an object as purely green, it has to emit mostly green light and very little red or blue. But remember, stars are black bodies. They emit a broad, continuous spread of light. So a star that peaks in green is simultaneously blasting our eyes with tons of red and tons of blue light too. When our visual system gets hit with all three of those colors in perfectly balanced amounts, our brain does this mixing trick and simply interprets the combined signal as pure white. That is why green hot is physically impossible in nature. Because of the way our human eyes work, green hot will literally always be perceived by our brains as white hot.
Isn't that just incredible? The absence of green stars isn't some failure of the universe, it's literally just a quirk of human physiology. So the really important takeaway here is this. 100% of stars carry a completely unique color signature. Even if our eyes stubbornly blend the middle of the spectrum into white, astronomers can use precise filters to measure exactly where a star's seesaw is tilted. Color becomes this incredibly powerful diagnostic tool that reaches all the way across the cosmos. By decoding these specific colors, astronomers can unlock the secrets of the universe without ever having to leave Earth. First off, a star's color gives us its exact surface temperature and energy output. But it goes way deeper than that. As stars age and start running out of their nuclear fuel, their temperatures change. That means their colors dynamically shift, which allows us to actually track a star's evolutionary stage and figure out how old it is. Plus, if astronomers know a star should be blue, but it looks slightly reddish to us, that tells them something amazing about the space in between. It means there are massive clouds of interstellar dust sitting between us and the star, scattering away the blue light and only letting the red pass through, very much like how a sunset works here on Earth.
So the next time you step outside on a clear night and you look up at that vast expanse of little white dots, I really hope you see them a bit differently. Remember that you are looking at an absolute cosmic palette of blazing blue supergiants, moderate white-hot suns, and ancient cool red giants. Every single star is out there broadcasting its own temperature across light years of space, painted in a color that tells the unique story of its life. So I leave you with this final thought. The next time you find yourself wishing upon a star, take a second and ask yourself, what color is it really? Thanks for joining me on this explainer, and keep looking up.